Welcome to this explainer. Okay, let's dive right into this. I want you to think of an ancient samurai. A master warrior doesn't just swing a sword wildly hoping to hit something. They move with absolute precision, intense discipline, and highly structured strategy. Every single strike is calculated. Every step has a purpose. Today, we are bringing that exact same warrior wisdom directly to modern exam strategy. We are talking about Cambridge physics. Whether you're building your foundational knowledge in IGCSE codes like 0625, 0652, 0654, 0972, or 5054, or you're stepping up to the absolute big leagues with Cambridge AS and A-level physics, specifically syllabus 9702, the battlefield is exactly the same. Today, we are going to look closely at the foundational concepts that trip up literally thousands of students every single year. We're talking about SI units, base quantities, derived units, prefixes ranging all the way from pico to tera, and the absolute non-negotiable vital concept of homogeneity. This isn't just a review. This is a masterclass in not just knowing your physics facts, but deploying them strategically to slice through exam questions with absolute precision. We are going to completely transform the way you look at a blank exam paper. You're going to stop reacting and you're going to start attacking.
So here is the big question. Why do students drop easy marks on fundamental SI units? I see this happen all the time. And honestly, it's heartbreaking. Imagine studying for months, mastering incredibly complex quantum mechanics, completely wrapping your head around the deep mathematical nuances of Kirchhoff's laws, only to step into that high-pressure exam hall and drop an entire grade boundary because of a silly unit prefix error. It's a trap, and it catches even the most prepared, straight-A candidates completely off guard. To really illustrate this, let me introduce you to two archetypal students we see in literally every single exam session. Let's look at a real Cambridge physics past paper question. We'll use a classic from code 0625 as our baseline. First, we have Alex. Now, Alex overloads their exam paper with raw physics facts. Alex has memorized every single textbook definition, but when it comes to the paper, they provide absolutely zero analysis. They just dump all that raw information onto the page, crossing their fingers and hoping something sticks to the mark scheme. Then, on the other hand, we have Sam. Sam actually understands the physics really well, but Sam rushes. Sam completely misses the specific command word requirements in the question. Sam doesn't realize the massive difference between a command word like state and a command word like explain. When we look at their flawed answers side by side, totally covered in the examiner's dreaded red pen marks, the root cause is almost always exactly the same, a fundamental failure to respect the foundational elements. They ignore the SI units, they gloss over the fundamental base quantities, and they lose easy, guaranteed marks.
Section 1. The examiner's warning. Top 3 pitfalls.
Now we enter the problem phase of our strategy framework. We aren't just guessing what goes wrong out there, we are looking directly at the hard data from the Cambridge Principal Examiner reports. Listen to me, these reports are the ultimate cheat codes. The examiners literally tell us, point blank, exactly what students are doing wrong year after year, yet candidates keep walking right into the exact same traps. If you want to master the paper, you have to know where the landmines are buried. Let's break down the top 3 pitfalls straight from the examiner's desks, because raw facts just aren't enough without strategic application. First up, confusing cause and effect. In physics, the sequence of events absolutely matters. When defining derived units or explaining physical phenomena, students frequently mix up the catalyst with the outcome. For instance, a resultant force causes acceleration. Acceleration doesn't cause a resultant force. It sounds simple right now, but under exam pressure, students flip this constantly. Second, forgetting format and presentation. This sounds trivial, I know, but it bleeds marks like you wouldn't believe. We're talking about significant figures, crystal clear working out, and, most importantly, stating your final answer with the correct explicitly written SI unit. A number without a unit in physics is absolutely meaningless. It's just a floating digit. Third, providing answers not specific to the given context. If a question asks about derived units in the context of a specific complex electrical circuit, giving a generic rote-memorized textbook definition without actively applying it to the circuit on the page will cost you the mark. You have to tailor your knowledge to the specific battle you are fighting right then and there. And hey, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
That brings us to a massive flashing red light. Examiner alert. Always define terms before using them in extended responses. The principal examiner reports consistently reveal that candidates completely confuse key terminology.
If you start throwing around terms like work done or potential difference in an extended multi-mark response without clearly anchoring them to their fundamental definitions and base units, the examiner simply cannot award you top marks. You have to prove you know the basic building blocks. This is exactly where we introduce the PEEL framework to structure your answers. PEEL stands for point, evidence, explanation, link. Top students don't just write paragraphs, they engineer them. First, make your point. State the physical principle clearly. Next, provide your evidence, which is your defined term, your base unit, or your formula. Then, offer your explanation. How does this formula apply to the specific system in the question? Finally, link it all back to the specific command word the examiner used. By using PEEL, you automatically define your terms right at the evidence stage, completely neutralizing this examiner alert and locking in those marks.
Section 2. Core Principles. Building the Architecture.
The entire theoretical foundation of physics rests on highly precise definitions, crystal clear causal relationships, and seamless integration across different syllabus areas. Mastering physics requires a deep, structural understanding. It's not just a random, chaotic collection of formulas you crammed the night before. It is a beautifully interconnected web. And the vital threads holding that entire web together? Your units and quantities. Candidates who can confidently reference these cross-topic connections achieve significantly, noticeably higher marks. So, the crucial starting point is drawing a hard, undeniable line between these two distinct concepts, base quantities versus derived units. Base quantities are your fundamental independent physical quantities. They are the absolute bedrock of the universe's measurable properties. You cannot break them down any further. There are 7 of them in the SI system. Mass, measured in kilograms, length, in meters, time, in seconds, electric current, in amperes, thermodynamic temperature, in Kelvin, amount of substance, in moles, and luminous intensity, in candelas. You must know these inherently, like the back of your hand. On the other hand, derived units are combinations of these base quantities. We create them by mathematically multiplying or dividing the base quantities to measure other variables. Take force, for example. The standard unit is the Newton, but a Newton is not a base unit. Because force equals mass times acceleration, the derived unit broken down into base terms is actually kilogram meters per second squared. Recognizing this specific relationship is exactly how you build those cross-topic connections. If you understand exactly how a joule breaks down into base units, suddenly the concepts of work, energy, and thermodynamics all start speaking the exact same underlying language.
Now, I want to challenge you right now to actively engage with this. Don't just sit back passively. Let's build a rock-solid mental anchor for these specific definitions right this second. Memory hacks are true strategists' best tool. I highly recommend creating a mnemonic using the first letters of the key terms for those 7 base quantities. For mass, length, time, current, temperature, amount, and luminous intensity, that's M, L, T, I, theta, N, J. You could use something absolutely ridiculous like many large tigers can tolerate all insects. I know, it sounds totally silly, but in the incredibly high-pressure environment of the exam hall, when your adrenaline is spiking and the clock is ticking down, a simple memory hack like this can instantly recall the structured data you need to secure those marks. This is a key part of our physics success blueprint. Find a mnemonic that works for your brain, write it on the inside cover of your notebook today, and never ever forget it. And listen, stop scrolling. Subscribe to our YouTube channel, Ace the Exams at acexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to acexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Section 3. Decoding Prefixes and Homogeneity.
Let's move the analysis forward and look at how we scale these units and rigorously verify their physical validity across complex equations. In Cambridge Physics Syllabus 9702, you absolutely must demonstrate total mastery of these fundamental principles. Top-performing students exhibit a connected, highly conceptual understanding that they can instantly transfer to completely unfamiliar, highly complex contexts. Homogeneity, in particular, is your ultimate self-checking mechanism during an exam. If an equation is homogeneous, it means the base units on the left-hand side perfectly mathematically match the base units on the right-hand side. It proves beyond a shadow of a doubt that your physical model is valid. Now, let's step into our interactive workshop. Consider this, Challenge 1, the data scan. I want you to imagine a 60-second visual timer right now. Scan the prefix scale in front of you, running from pico, which is 10 to the power of -12, right up to tera, which is 10 to the power of +12. Pico, nano, micro, milli, centi, deci, kilo, mega, giga, tera. Top-performing students rapidly decode these prefixes without a second thought. When they see a capacitance written as 4.7 picofarads in a dense data table, their brain instantly automatically translates that to 4.7 times 10 to the -12 farads. If you miss a single micro in a multi-step calculation, your final answer will be off by a factor of 1 million. A literal million! That completely destroys your final answer mark. Time's up on the scan. You must memorize this table forwards and backwards.
Section 4, Technical Methodology, the Method Mark Strategy.
Now that we have our core elements clearly defined, let's introduce the solution phase. The academic benchmarks for Cambridge require highly logical, incredibly structured reasoning. The assessment framework heavily prioritizes analytical depth over superficial breadth. What this practically means for you is that marks are heavily awarded for a clear, logical process, even if your final answer has a minor, accidental calculation error at the very end. This right here is a standardized procedural framework designed specifically to guarantee you scrape every possible mark, even on the absolute toughest, multi-layered questions. Let's dive into Challenge 2 of our workshop, Find the Flaw. I'm going to energetically guide you through this 5-step blueprint, and I want you to think about where our friend Sam went wrong earlier. Step 1. Deconstruct the question. Highlight the command words immediately. Is it asking you to determine, show that, or derive? Each word demands a totally different level of mathematical rigor. Step 2. Extract relevant data. Pull the numbers out of the dense paragraph, convert all those prefixes to standard form immediately, and write them in a clear, vertical list. Step 3. Select your analytical framework. Write down the core formula you are using. Listen to this. Just writing the correct unarranged formula on the page often secures your very first method mark. Step 4. Execute with clear notation. Show your substitutions explicitly. Do not do the math entirely in your calculator. Write the substituted values down. Step 5. Present with correct terminology. Provide your final answer, rounded to the correct significant figures, alongside the explicit SI unit. If your current process has a flaw, it's because you are skipping one of these steps. This sequence is absolutely non-negotiable if you want that A or A star.
Let's look at the stark visual contrast here. On the left side, we have the superficial answer. This is exactly how our student Sam writes. The calculations are incredibly rushed, there are no structural headings, the numbers are just floating randomly in space, and the vital final unit is completely missing. The examiner has to hunt around the page for the answer, and let me tell you a secret. Examiners absolutely hate hunting. This superficial answer hemorrhages easy method points. Now, shift your focus to the right side, the analytical answer. Notice how the red pen marks of failure transform into the green check marks of success. This is where Challenge 3 comes in, speed writing. Imagine a 30-second timer counting down right now. Could you mentally draft this perfect response? This answer expertly incorporates the Peel framework, point, evidence, explanation, link, specifically adapted for physics calculations. It has proper headings, correct terminology, crystal clear annotations, and steps that flow logically, beautifully down the page. Examiners love to reward this. By formatting your answer cleanly, you aren't just solving a math problem, you are communicating your total competence directly to the marker. You are showing them, without a doubt, that you are a master of the subject.
Section 5. Critical Analysis, Evaluation Level.
For our final act, let's shift our focus entirely to the absolute highest tier of the assessment framework, the evaluative level. Up until now, we've talked mostly about calculating and describing, but critical analysis is exactly where you separate yourself from the rest of the pack. Higher-order assessment objectives demand that you don't just calculate a raw number, but that you evaluate its actual validity in the real world. This is what evaluative level mastery looks like. It's the core of our complete physics answering system. You need to master 3 rules: command word decoding, Peel framework application, and the time management matrix. But at this highest level, when you look at an experiment or a derived equation, can you evaluate alternative methods? Can you compare different approaches to minimizing percentage uncertainty? Crucially, can you identify the hidden limitations and assumptions made in your calculations? For example, if you calculate the final velocity of a falling object using basic kinematics, evaluative mastery means explicitly writing down, this calculation assumes air resistance is completely negligible and acceleration due to gravity remains perfectly constant, which introduces severe limitations in a real-world, non-vacuum context. Evaluating the quality of your evidence, deeply understanding alternative interpretations, and justifying your final recommendations based on solid physical principles, that is the true hallmark of an elite A-level student. It proves you understand the very boundaries of the physics you are applying.
I want to give you this precise syllabus insight. The assessment framework prioritizes analytical depth over superficial breadth. Cambridge does not want you to memorize 1,000 disjointed random facts. They really don't. They want you to take a handful of fundamental foundational principles, like your SI base units, your flawless prefix conversions, and the unbreakable law of homogeneity, and apply them deeply, rigorously, and carefully to complex, entirely unseen scenarios. It is entirely about the depth of your analysis and the undeniable clarity of your methodology.
So, I leave you with this final provocative thought, something that should force you to completely rethink your entire study approach. Are you just memorizing formulas?
blindly crossing your fingers and hoping the exact same questions from the 2018 paper show up again? Or are you actively building a structured, analytical framework that can withstand absolutely any curveball the examiner decides to throw at you? Stop memorizing blindly and start mastering the architecture of the paper itself. Listen closely. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but that only happens if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams at @acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @theaceexams_IGCSE and click that bell. Don't let another exam pass you by. Before you go, drop a comment below with your exact target grade for physics and the absolute biggest challenge you're currently facing. Our team responds to every single comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.